Welcome to the tutorial on design of a binary multiplier. Here we will design a multiplier for positive binary numbers. The binary multiplication will require only shifting and adding process. So this particular example shows how each partial product is added as soon as it is been formed. So this method will eliminate the need for adding more than two binary numbers at a time. So if you observe, you can see we have considered two numbers 13 and 11. The number 13 is the multiplicand and the number 11 is the multiplier. So initially the LSB bit is being multiplied with the number 13 in order to obtain the result. Then we are going to multiply the second bit with the multiplicand to obtain the result with a shift operation that is being done. The result of these two are going to be added. Next, we are going to multiply the number in the third position with the multiplicand to obtain the result. So this result will be added with the previous result to obtain the new addition result. Finally, the fourth bit of the multiplier will be multiplied with the multiplicand to obtain the result and will be added to obtain the final product term, which is equivalent to 143 in decimal. So these intermediate steps or these intermediate multiplication operations or the products that we have obtained are termed as partial products. And in this method, we are continuously performing shifting and adding operation so that we can eliminate the need for adding more than two binary numbers at a time. So in this particular example, we have considered the multiplication of 4-bit numbers. Therefore, we will require a 4-bit multiplicand register, a 4-bit multiplier register, and a 8-bit register to store the product. So let us look into the block diagram for the binary multipliers. So here is the block diagram of the binary multiplier, wherein I have the 4-bit multiplicand, the 4-bit multiplier register, and a total of 8-bit register to store the product. This product register serves as an accumulator to accumulate the sum of the partial products, and instead of shifting the multiplicand left each time before it is added. So this method is more convenient to shift the product register to the right each time. So as you can see in the block diagram, the 4 bits from the accumulator and the 4 bits from the multiplicand register are connected to the adder inputs, which are indicated by the arrows in the diagram. The 4 sum bits, that is these 4 sum bits, and the carry output from the adder are connected back to the accumulator. This particular adder, the adder will calculate the sum of its inputs, and when an add signal, which will be represented as AD, occurs, the adder outputs are stored in the accumulator by the next rising clock edge, thus causing the multiplicand to be added to the accumulator. An extra bit at the left end of the product register will temporarily store any carry C4 that is being generated when the multiplicand is added to the accumulator. When the accumulator is shifted right side, the input to the bit 8 of the accumulator must be 0. Then a following shift will shift the correct value into the 7th bit of the accumulator. Because the lower 4 bits of the product register are initially unused, we will store the multiplier in this particular location, that is 0, 1, 2 and 3 instead of a separate register. As each multiplier bit is used, it will be shifted out to the right end of the register to make room for the addition of the product bits. A load signal that is available here will load the multiplier into the lower 4 bits of the accumulator and at the same time will clear the upper 5 bits. The shift signal, which is represented as SH, causes the contents of the product register including the multiplier to be shifted one place to the right when the next rising clock edge occurs. The control circuit puts out the proper sequence of add and shift signals after a start signal, which is represented as ST, has been received. That means ST has to be equal to 1 for proper addition and shift operation to occur. If the current multiplier, that is represented as bit M, will be equal to 1, the multiplicand is added to the accumulator followed by a right shift. If this particular multiplier bit is 0, the addition is skipped and only the right shift occurs. So let us understand the working of this particular block diagram in much detail, considering the same previous example of multiplying 13 cross 11. So here the multiplication example that we considered, 13 cross 11, has been reworked to show the location of the bits in the registers at each clock time. So what we are going to do is, if you observe the accumulator is having a total of 9 bit positions, and the lowermost bits or lowermost 4 bits correspond to the multiplier, and the remaining bits are going to store the result of your addition. So initially we are going to load the contents into the product register. So as you can see, so the product register will be storing the multiplier, and in our case we are considering 1011 to be the multiplier. So this 1011 will be stored in the lower bits of the accumulator, and the higher bits are going to contain all zeros. Since the controller was initiated with M equal to 1, we are going to add the higher bits of the accumulator with that of the multiplicand. On addition, we will get this particular result, which is being highlighted in yellow color. Now we need to perform one shift to the right. So when we perform one shift to the right, you can see the current value of the accumulator. So the accumulator is having at the various bit positions, this will be the 0th position, this will be the first position, second position, third position, fourth position, 5th, 6th, 7th and 8th. So the 8th position is having an extra 0. Rest of the bits have been shifted. Now you are going to add the multiplicand with the shifted value of the accumulator. So on addition, you get a new result that will be retained in the accumulator. The addition operation has to occur whenever the value of m is equal to 1 and you are going to perform a shift after that. So now since we have obtained the addition result, we are going to perform a shift again with the 8th bit position having a 0. So this 1 will come here, this 0 will come here, this 0 will come here, this 1 will come here, 1, 1, 1 and this 0. Now again we are providing m to be equal to 0. When we provide m to be equal to 0 to the controller, we are going to perform only shift operation. So because of that, as you can see, you can obtain in the 8th position again a 0, 7th position will be 0 and these remaining bits till here will be retained at this point. Now we are going to provide m to be equal to 1 and now we can add the contents of the accumulator with the multiplicand. So on addition we will get the result 1 0 0 0 1 1 1 1 1 and because m was equal to 1 we need to perform both addition and shift. So we will be performing the shift operation with the 8th position having a 0. So the final result that we obtain is this, which is equal to 143, same as that of the one that we have seen in the beginning. So from this example you can clearly see that the partial results or partial products that we had obtained in between were all stored in the accumulator, that is in the position 8, 7, 6, 5, 4, 3, 2, 1 and 0. And during each shift position the 8th bit was made equal to 0. Next we will look into the state graph for the control circuit. So the control circuit that we have seen in the block diagram must be designed to output the proper sequence of addition and shift signals. And in this case there are various notations that are being used. So we have m/ad, which means if m is equal to 1 then you need to output ad to be equal to 1 and other outputs have to be 0. m-sh means if m dash is equal to 1, which actually means m equal to 0, then the output shift will be equal to 1 and other outputs will be 0. S0 will correspond to the reset state and done signal corresponds to the termination of the multiplication process. Load signal will cause the multiplier to be loaded into the lower bits of the accumulator and the upper bits of the accumulator to be cleared for the next rising clock edge. So let us begin with the process. So initially we have the state S0. If no start signal has been initiated, that means we need to remain in the same state and we are going to come back to the state S0. If a start signal has been initiated, we are going to load the contents into the accumulator. That means in the loading process, we are going to load the lower bits of the accumulator with the multiplier and the upper bits of the accumulator will be all zeros. Now you are in the state S1. So the lower order bit of the multiplier, that is m, will be tested. If m is equal to 1, an add signal is generated and then a shift signal is been generated into S2. If m is equal to 0, a shift signal is generated because adding 0 can be omitted. Similarly, in the state S3, S5 and S7. So each time you are going to test for m, to determine whether to generate an add signal followed by a shift or just a shift signal. A shift signal is always generated at the next clock time following an add signal which corresponds to the states S2, S4 and S6 and S8. After 4 shifts have been generated, all 4 multiplier bits have been processed and the control circuit goes to the done state and terminates the multiplication process. One of the important things that we need to note here is that the done signal cannot be turned on in state S7 or S8 because the last shift does not occur until the next active clock edge occurs. The last shift occurs at the same time the transition to the state S9 occurs. The control signal SH enables the shifting to occur to the next rising edge, but it does not cause the shifting to occur. So in general, if a control circuit or if a control signal is turned on in state Sn, the resulting action does not occur until the next active clock edge takes the circuit to the next state. So this particular state S9 could be eliminated if it was acceptable to turn on the done signal in the state S0 when St was equal to 0. So let us look into the operation of the multiplier using a counter. From the block diagram that we have understood, there exists a control which is required because it performs mainly 2 functions, that is, it generates add or shift signals whenever it is required and counts the number of shifts. If the number of bits is very large, it would be convenient for us to divide the control circuit into a counter, and add and shift control can be used like the way it is shown in the figure A. So in this example also we are going to multiply 13 with 11 and we are going to make use of 3 states S0, S1 and S2 of the control circuit. So for this particular control circuit, we can derive a state graph for the add shift control which will test M and the start and outputs the proper sequence of add and shift signals. Then we will add a completion signal K as shown in the figure C from the counter, which will stop the multiplier after the proper number of shifts have been completed. So to begin with the figure B, initially starting with the state S0, when the start signal is not provided, that is St is equal to 0, you are going to remain in the state S0 itself. When a start signal is given or received, that is St is equal to 1, a load signal is generated. So you are going to load the contents into the accumulator. So in this particular state S1, if M is equal to 0, a shift signal is generated and the circuit will stay in the state S1 itself. If M is equal to 1, an add signal is generated and the circuit will go to the state S2. In the state S2, a shift signal is generated because the shift always follows a add. Back in S1, the next multiplier bit M is tested to determine whether to shift or add and then shift. So this particular graph will generate the proper sequence of add and shift signals, but it does not have any provision for stopping the multiplier. So in order to determine whether the multiplication is completed, a counter is incremented on the active clock edge each time a shift signal is generated. So if the multiplier, say for example, is of n bits, a total of n shifts are required. So let us design the counter so that the completion signal K is generated after n minus 1 shifts have occurred. When k is equal to 1, the circuit should perform one more addition if necessary and then do the final shift. The control operation has been shown in this particular figure. So if you look at the figure C, the state graph is similar to the one that is shown in the state graph B with an additional k to indicate the completion signal. So from this what we can understand is that as long as k is equal to 0, this particular state graph is going to be same as that of the state graph B. When k is equal to 1, the circuit should perform one more addition if necessary and then do the final shift. So to explain in much detail, when you are in the state S1, if k is equal to 1, we will test m as usual. If m is equal to 0, we will output the final shift signal and stop. However, if m is equal to 1, we will add before shifting and go to the state S2. In the state S2, if k is equal to 1, we output one more shift signal and then go to state S3. The last signal, shift signal, will reset the counter to 0. At the same time, the add shift control goes to the done state. In this particular example, we have considered both the multiplier and the multiplicand to be of 4 bits. So the value of n will be equal to 4 and we will require a 2-bit counter. So for this particular example, let us look into the operation of the multiplier in the form of a table that shows the multiplication of 1101 with 1011. So initially at the time t0, the control is reset and waiting for the start signal to occur. So you can see that all the bits of the product register are zeros because the start signal has not been initiated. At the time t1, the start signal will be equal to 1 and the load signal is generated. At the time t2, m is equal to 1, so an add signal is generated and you are going to add the contents of the accumulator with the multiplier, and when the next clock occurs, the output of the adder is loaded in the accumulator and the control signal will go to the state S2. So at the time t3, SH signal is generated and a shifting will occur. So you can see here, this part is the result of the addition process and this is the 8th bit position which is equal to 0. And in this case, m will be equal to 1 and the counter will be incremented from 00 to 01. So at the time t4, the counter is incremented because a clock has occurred and m will be equal to 1, so an add signal is generated. Moreover, the adder output is loaded into the accumulator at the next clock edge. So at the time t5 and t6, shifting and counting will occur. At the time t7, the 3 shifts have occurred and the counter state will be at 1 1. So the value of k will now be equal to 1. So at the next clock, the final shift will occur. Counter will be incremented to state 0 0. This is the final shift. The counter is incremented to 0 0 and at the time t9, we are going to generate the done signal. So this particular operation of the multiplier using a counter can easily be expanded to 8, 16 or more bits simply by increasing the register size and the number of bits in the counter. The add shift control will remain unchanged.